Hello everyone, it's May 17th. Alright, let's get right into it. What do we have today? It's critical connections in the network. Alright, oh no, that's not this one. No, it's not this one. Oh, my bad, it's this one. I opened too many. I've done this before. Let's take a look. Oh my. Ooh. Alright. Let's see. There are n servers, numbered from 0 to n-1, connected by undirected server-to-server connections, forming a network where connections I represents a connection between A and B. Any server can reach other servers directly or indirectly through the network. So it's connected. It's a connected graph. A critical connection is a connection that, if removed, will make some servers unable to reach some other server. Return all critical connections in the network. So this is a... Huh? I don't remember if it's an interview question, but this is a very classic questions in graph theory, which I know how to solve in the past, but graph theory has a lot of algorithms, and you just tend to forget.
Distributed system?
It's not. It's just graph. It's graph theory. Honestly, it's okay. So in the first one, we say 1, 3 is the critical one, because if you do this, 3 cannot be connected, but any of the others is not. So no repeated 10 to the 5th. I don't remember how this is solved. Honestly, I don't. But I might have some vague idea. If you think about it, what will happen if an edge is a critical edge? It means if you cut it, right? If you cut it, then something else cannot be reached. All right? Let me think. Probably the draw. Let me get my pencil and paper. A very simple example is we can do, two triangles. Okay, two triangles connected together. If we can solve this, we might be able to solve the rest. So we have two triangles, and we have another triangles, and they connected. So the critical path is going to be the node that connect the two. And how are we going to solve this? Well, thank you. All critical connection. If we go through all the connections, can we make a quick judgment whether this connection is critical or not? But if you break a connection, then of course you cannot go directly from this node to that node. And then the question is, can you reach that node from, let's say, a different route, right? Okay, let's say if we break this and we want to A critical connection means from one node to the other node, there's only one path. If we have multiple paths, then it has to be only one path. You cannot just check how many paths there are from one node to the other node. No idea. No idea at all. Let's go right into it. Hint. Oh. What's the purpose? Like, I have no idea what this Tarjan's algorithm is, so we have to look it up. Maybe looking it up, I will be able to remember it. Strongly connected components. Let's take a look. Tarjan's strongly connected components is an algorithm for finding strongly connected components of a directed graph. Produce partition into the graph strongly. What are strongly connected components? Every vertex is reachable from every other vertex. And then produces a partition of the graph vertices into the graph's strongly connected components. Each vertex of the graph appears in exactly one of the strongly connected components. Any vertex that is not on a directed cycle forms strongly connected components all by itself. What is low link? It's the lowest. Everyone has a index, right? Everyone has an index, and the smallest index of any node on the stack known to be reachable from V through V's DFS subtree, including V itself. So it's on the current subtree that we're traversing. What is the smallest node reachable by me? Okay, so I will do this, and then what? And then every time it's not visited, I visited an index increment 1, and then if W the index, which means haven't visited before, now I visit it, and then after that, because V and W are on the same path, so we can call W.lowLink, which is the low link of W, and I will compare the two to make sure V.lowLink points to the smallest index that V can reach. Okay, so that's that. Else, if is defined and it's on stack, right? It's on stack. So we're visiting a node that's already on stack. Current strongly connected component. If W is not on the stack, if W is not on stack, then VW is the edge pointing to an SCC already found. If W is not on stack, which means W is in the previously found strongly connected components, and now mine can connect there, it must be ignored. I don't understand. If W is, then VW is an edge pointing to an SCC already found. It's pointing to a SC strongly connected already found. Which means we have a strongly connected component, which means everybody can reach everybody else. But the thing is, everyone can reach everyone else in the current. Right? We're trying to find a strongly connected component. Put in the original graph because it's already strongly connected. It's a strongly connected component already. So if we set and then we start going, v.lowLink is equals v.index. V is root. So it means as I was traversing through from any node, traverse, right, traverse. We'll update on this. Here, then we go here, and then we update on this. Keep going, and this one, update. So what? It's not gonna go back. You keep going. Keep going. And we're not outputting anything. Here we are. We outputted the entire thing as a strongly connected component. How do I use this algorithm? Hold on. It doesn't make any sense. A subtree. It's on the stack, which means it has been visited before. A low link is the lowest link I can reach in my subtree. A back edge. It is something I already visited before. And now here, and now it's a back edge. Okay, it makes sense. I kind of understand, but still, how does this help us? Because the entire thing is strongly connected. we can just like take something off and try to see how many strongly connected components are there. Yeah, that's what I think is if you take one away and you see how many components are there. And if there are, well, what's the purpose? What's the point of doing this then? I think if we start from here, I will go here, right? And I'll go here, and then I'll go here, and then I'll go here. I'm trying to see which one is the smallest. And then if this by itself, right? If everyone has done already, yeah, so we have a path, this one, this one, this one. No, they're indices. Okay. That means from this, the minimum we can reach is this and this. Then that's not the root. And this points to this. So this one will point into this. And I come here. This one will point to this. Because this one's on the tree. But that's not a subtree. What? Yeah, I don't know. I need to check another one. That means that a strongly connected component has to be the maximum subgraph satisfying the condition. Are you saying we'll turn the original graph into a directive? So each edge we will have one direction. and which direction to choose. The lowest reachable from you, which is not the part of another SCC. The lowest that's reachable. Six, six. Seven. Yeah, because out of 5. Because this one's already visited, that's in the path. So we'll update it to 4. Now I find a strongly connected component. Two is 2, 2, right? And 4 become 1. 3 become 1. Are we saying we're going to start from any node, right? And there's no guarantee. Start from here, we come in here, and then you say once we do that, don't go back. I still don't know. With a hint, still no good. Because the other one works on directed graph. This is an undirected graph. I don't know. This entire thing is a connected graph, strongly connected. If we say you cannot visit the node, you can only go forward. If we can only go forward, this is by itself. Here, then I go here, then I go here, then I go here. Basically, just we arbitrarily turn an edge into a directed edge. But if we go this one by itself, and we do this one, maybe it will work. Yeah, it will work because the edge is defined when I'm traversing it. And since I can always traverse, like however I traverse, if I traverse to a certain point and I got stuck, then we just get stuck. All right, let me go back to my other example. So from here, I just simply traverse. I say, I don't know, traverse. Oh, we've already gone. That's a component. All right. And then how does this will be a component out. All right, we'll just pop this one out. And then we'll go back here. Okay, but how do I find the edge then? Color them. Put them into different colors. Because they all have a low link. Everyone has a low link. So we just traverse through all the edges and find if two things have different low link. Then okay, I'm ready to give it a shot. All right, how much time has passed? 38 minutes. It took a while to understand the problem in the first place. All right, so the strategy is to have a visited. So instead of like just finding something on the stack or not on the stack, we will have a visited, which can turn a visited set, which you can turn. Well, actually, it doesn't have to be a visited set. Just anything that's visited, we cannot visit again, right? So basically, we can just put low edge, a low link is our visited. And in the original algorithm, if it's on the stack, right? We visited if it's not on the stack, and if it's on the stack, we'll update. Right? We'll update. Actually, when they update, It's on the stack. Yeah, I don't think it's low link, right? No, it is. I mean, if we find something that's on it, if we find something that's on it, and I still don't understand that. If you find something that's on the yeah, because at this point it's 5, 5, 6, 6, 7, 7. And if we go back here, it doesn't matter. It'll be home 5. The lowest I can reach. V is in the stack, which it means it's on the path, right? It's on the path. Then I cannot, because the low means the lowest that this node can visit. But now when I go back here, right, that doesn't mean it's not like if, that means we start from something, right, and then we go back to you, right? We go back to you. This low might point into something in the past, but I cannot point him back because I cannot go. It has to be my subtree, right? What I can lead to, and then it doesn't go back. So yeah, so it has to be because this V it's already in the stack, which means this is something happened in the past, right? It's some node that happens in the past. Now I reach it, so I have to use disk, right? I have to use its index, because if not, then we're reaching something that can reachable from V, and the node reachable from V is not the same than the node reachable from U, right? The V can be reachable from other things, right? Like V, we can divert, right? On the one side, you can have a low. On the other side, it can be like there, right? And then it's nothing. Now we just go back. Actually, it's not gonna go back. It's just gonna pop, 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 pop. Yeah, it could be like this. We divert, pop, and then we have something, and then out. And that's what this V can reach. Actually, no. So we reach back. We want this V to be the root. If we go something smaller than V, then V is not a root. Then we'll never find a root. because we'll update everybody else to v. If we go v, then everybody else will be v. And if we point to something that's not v, then everybody else will be, and then we can have like something like that, which is not. That's a strongly component. That is not. Right? Is that right? We'll loop and we'll loop back. Yeah, if we have a loop and we loop back, so I think the better explanation is this just means we looped back. Right? We looped back. When we looped back to v, then v gotta be the root. When we loop back there, right? We loop back. It's a path that just keep going, going, going. And eventually we hit a point where we looped back. And then we have to set that one. The looped back one is the smallest that my subtree can reach. So, what do we want? I think we try to write it. We have to create a adjacency list. Okay, for AB. A. Doesn't matter. Okay. Node, right? Visited. Node visited, and then we will have a low links and indices. Okay. Okay, here's what we do. So we're visiting this node. Whenever a node comes in, we're gonna set low links node equals node, indices node equals node. Okay? Actually, no. Indices we're gonna have self.index. This is gonna be self.index. Alright, that's the index. Index keep going up. Then what? Then we simply say index going up, and then we say for neighbor in adjacency list node, right? Say if indices neighbors is smaller than 0. No, we haven't done it yet. Then we can say DFS index. Oh, one more thing. Visited.add node. Right, visited.add node. I want to visit once. Actually, in this case, we can just say visited equals a set. I don't have to pass it. Right, so visited, so node visited, and now we say neighbor in if and neighbor not in visited. then I or DFS neighbor, right? Or DFS neighbor, and afterwards I'll say low links node equals the minimum low links node and low links. That's my subtree neighbor. Out of neighbor is in visited, and just else. All right. Oh, do I even need visited? No, I don't need. Just indices. Because we said every node will be visited only once. Right, so if I visited, then I don't visit you again. Oh, hold on. It has to be on the current path, right? All right, it has to be on the current path. Yeah, we do need to have a stack. So we do need a visited, which can serve as a stack. But hold on. I can use the low links because everybody will be having the same low links. Else it's visited before and it's on the current stack. Or you just visited. Right? Wait, hold on, let me just check again. on the stack. I can use a set as well. And then we'll pop those out of the set. Oh no, it has to be a stack. Pop until here. And we don't pop anymore. Then we keep search. So we need a stack. And we need a set. Stack is going to be a list. And we need a stack set. All right, it's a stack. It's a set for stack. So instead of this, I'm going to say stack.append node, stack set.add node. So if not visited before, we visited elif neighbors in stack set. Right, that means it's on the current path. Then we say low links swim, low links node, and indices neighbor, because it cannot go backwards. The neighbor is the we already go around. So yeah. So we check all of these. So for every node, we'll try to see what is the minimum node I can reach. Right, minimum node I can reach in my subtree. Right, minimum real node I can reach in my subtree. And eventually, I can say if low links node is equal to indices node. If these two are the same, right, then we simply just remove. We're gonna pop, right? How do we do it? We say while stack 0, no, -1 is not equal to stack. The top of the stack is not equal to the current node. Don't say stack.pop, stack set.remove, right? So we just pop until they're the same. And in that case, when they're the same, I'm gonna do this one more time. Right. So remove the entire thing that's on the stack, including this one, because that's the starting point. So remove all of this, so these are gone. And then that's it. Yep, and then we'll pop again. So that's that. And after that, we're done. Right, we're done with the current node. So this is our DFS. So we're gonna run the DFS. So I'm gonna call it DFS. We're gonna go through every single node, right? For node in range, and for each one, we're gonna call DFS node stack and set, right? We're gonna do that, and then actually, I'm gonna say if low links, if indices node is smaller than 0, then I do this, right? Okay. Now after running through each critical links are those that connect two groups, two subgraphs of different low link. So we're going to return, I'm going to say for AB in connections if low links A is not equal to low links B. If the two are not the same, right? If they point to different things, then we say, okay, A and B. Okay. How much time? Already 1 hour. This is a good problem, right? But the thing is, even if you do it another time, right now, I still won't be able to memorize or remember what the algorithm is. That's the sad thing. Simply don't know. Okay, so N connections, critical connections. Set is not defined. DFS missing. STK, STK set. Where? Neighbor. Okay, so we passed the first, but we failed the second. Why? 0 to 1. How is that possible? N is 2, right? And then we start, because it's smaller than 0, and we start link equal to 0, right? And their indices. Actually, indices. Yeah, indices 1. And neighbor was 0 equal to 1. So we go 1. Okay, so low links will be 1. Now, so that 0 will be in. Oh, my bad. If this, if indices, we're pointing back. Cannot point him back. Wait, hold on. It cannot be something cannot be my parent. That's what it is. It can be, yeah, it just cannot be my parent. It can be like my parent's parent, but cannot be my parent. So how do I know if it's, so we're just passing a parent, right? Say if neighbor is equal to parent, continue. Otherwise, this, and then parent will be this. Okay, so handle this. Try it. Doesn't look promising. What a wrong answer. Ugh. Expected none. My. You're not right. Maybe we need to consolidate it. Can I consolidate everything to the same low link? Yeah. We need this consolidation. Ensure that all nodes in the path Now consolidate. No links. All nodes in the path. Still not right, huh? This one maybe I can take a look. Yeah, it's actually fine. So without consolidation, it works. Screw this, I know. So without consolidation, it works, but with consolidation, it doesn't work. Let's draw it out. I have 0 to 1, 0 to 2, 0 to 3, 4 to 1, 4 to 2, 4 to 0. Alright, how would this one be wrong? Dang it. Now it is 0. Okay. And then low links. 0, 1, 2, 0, 1, 2, 3. Four. Actually, I need to know the stack. 0, 1, 4, 2, 3. Huh. How? 2 go to 3? No, 2 doesn't go to 3. Alright, this doesn't make any sense. What? Zero, 1, 2. 2 go to 0, 2 go to 4. Now node is 2. Node is 1. Yes. Oh, because 0 go to 3. Hmm. 0 go to 1, go to 4, go to 2. And then, yeah, that's it. Go to 2. And then 0 go to 3. But then we put on the same stack. We shouldn't put on the same stack. That's right. We handle this. Right, the last one is going to be 3. 0, 1, 2, 3. So these two are the same. What? My bad. That's the reason. Yep. Find the reason. Shop index. Oh my god. You're saying we do have to consolidate. We do have to consolidate. All the nodes on the current path. Consolidate all the nodes on the current path. Consolidate the low link to that of the root of the current path. Very, very tough. Very tough. Not only do I not know, do I not remember the Tarjan's algo, but I also struggle with adapting Tarjan, which is used on a directed graph, to this problem, undirected graph problem. Breakthrough is realizing that if we keep track, right, if we do not visit backwards towards parent, we can treat a undirected graph as a directed graph. Thus, Tarjan works. Another important thing is that we need to consolidate. They may have different, but why? All the nodes on the current strong current path to the same low link when the root of this path is discovered. This is to ensure that we can correctly label all the nodes that do not share any critical link. label the same value. Is it this plus e, whatever this is? Oh no, we don't want to discuss. Actually, I think it's all right. That's it. I don't want to keep going. Tough problem. See you guys tomorrow. Adios.